Thanks for coming out, everybody. I'd like to introduce to you our team here. To my right here, I have Boris McDaniel. I have Steve Kushka. I have Winnie Din. At the podium is Darren Parsons. To my left is Artem Tkach, William Sin, and Paul Sarmiento. My name is Nick Thorpe, and we are Minotaur Engineering. So we're going to present to you Micromouse. So a few months ago, we got presented with this problem to be in this competition. As you all know, Micromouse is an IEEE competition that started in the late 70s. The goal of this competition is to build a miniature robot to complete a 16 by 16 cell maze. And you have 10 minutes for each run. And in that 10 minutes, you want to find the center of the maze as quick as possible. So you map out, find the center, but then you want to race to the center. And the shortest amount of time is going to be your time, and that's going to judge if you win or not. Each can, like I say, each has 10 minutes. So our goal was to find the center of the maze as fast as possible. To do that, we chose to go with the DC power motors. We just decided, it's going to be hard, it's going to be challenging, but we also know that the shortest distance to the center of the maze is going to be the fastest. So with the DC motors, we'll be able to take advantage of the straightaways, and with some good controlling measures, we'll be able to make some good turns and navigate to the center. So as you can see, this was our vision right here. We decided to use a PCB chassis that's going to mount all apart the DC motor, the gyro, the batteries, the IR sensors. The IR sensors, as you know, are used as our eyes for the maze that tells us there's a wall in front of us if we're in the center of the cells. And our DC batteries, we're going to use little lightweight batteries, which are around about 180 milliamp, 7.4 volt batteries. They're real tiny, but they're going to give us just enough power to power those DC motors up to fast speed. And we're going to use a PIC32 microcontroller. So this is what we created, Minotaur 1 right here. As you can see, this is our actual first one built. We have another one built as well that we've been putting together. It's been quite a long process, but we're real proud of what we've accomplished with all with the time we've had. So I'd like to present to you a short little clip of what we've done so far so you can get an idea of what you're going to see on December 4th. My apologies. You guys just might have to come on December 4th and actually see it in operation. Is it going to play? No, it's okay. Well, I'll just pass it on to Darren Parsons and he'll explain to you the PCB chassis.
Thanks, Nick. I'll be talking about the microcontroller we selected. We selected the PIC32, and the reason why we chose this particular PIC32 is because it contained all the functions we need to utilize, such as 2 external timer inputs for our motor encoders, 4 analog inputs for our IR sensors and to monitor battery voltage, also SPI for the gyro, 7 GPIOs for our H-bridge, 5 for our H-bridge, and 2 for our user push button interface. And lastly, PWM for motor control. Next, to further elaborate on how the software is going to interface with the hardware, I'm going to pass it to Winnie.
Hi, I'm Winnie, and before my colleagues go into more detail about our hardware components, I'm going to give you a quick overview of how we're going to be taking that data from those components and processing it in our PIC. To get through the maze, our mouse is going to require a lot of feedback. We're relying very heavily on this feedback from our infrared sensors, our gyroscope, and our Hall effect encoders. To process the data from these components, we created an interrupt service routine that's going to run every 1 millisecond. And the data from our IR sensors and our battery voltage is going to be stored in our ADC buffer. So first we're going to check our ADC buffer for that infrared sensor data. And then next we're going to check the feedback from our gyroscopes and get the Z-axis rotational data. And after that, finally, we're going to check the data from our Hall effect encoders. And after getting all that data and processing it, we are going to update the distance traveled, our flood fill algorithm, and then make the necessary motor adjustments by changing the PWM duty cycles that we sent to our Motor 1 and Motor 2. To talk more in depth about our flood fill algorithm, William's gonna.
So like the other teams, we're using the flood fill algorithm, and the way it works is it just finds the minimum distance to travel between its position for each cell's position and the end goal. In this case, the goal is in the center. And so as the mouse moves through the maze, it's gonna look at all the walls in that maze, update a map, and then recalculate the distance. And then based on those distances, it just needs to count down from whatever value it's in to the next lowest value until it reaches the end goal, which is 0. And to explain a little bit more about how our infrared sensors work is going to be Arno.
Thank you, Willie. So in this project, we decided to use high-power SFH 4550 IR sensors. So the micromouse will be able to detect obstacles and successfully navigate within the maze. These sensors actually use light intensity to detect a change in the distance between micromouse and a wall. Because all the walls in a maze are predefined with white color, these sensors actually gave us pretty good results. Our micromouse is equipped with 3 pairs of sensors. There's 1 front pair and 2 side pairs. Each pair has an emitter and a receiver. Front pair is used to detect walls in the front, so the micromouse will be able to speed up or slow down when it is necessary. And our side sensors are used to keep the micromouse in the center of a cell. In addition, to help us to detect also a no sidewall condition in order to prepare the micromouse for a possible turn if one of the 2 conditions is satisfied. A, might be a wall in front of the micromouse, or B, the cell that is in the front, the cell that is currently in the front of the micromouse has been mapped as visited by our mapping algorithm. Now let's take a look at those 2 graphs. These graphs represent actually data captured by our receivers. As you can see, in certain regions, once the micromouse gets closer to the wall, there is a rapid voltage change in that region. We tuned if you look at the upper graph, we tuned our front sensor to work effectively in the range of approximately 15, 16 centimeters up to 5 centimeters. And on the graph below, you can see that we tuned our side sensors to work effectively in 7 to 1 centimeters. In those particular regions, you can see nice voltage swing that provides us with good range of values to work with, and we can use those values to pass it to the ADC. Since our receivers take care of ambient light automatically, we decided to have all of the meters on all the time at the same time. We decided not to switch them on and off on each interrupt service routine. This actually provided us with a better, more accurate positioning data, and as well reduced significantly the complexity of our software. Once the micromouse is powered on, let's take a look at this picture. Once the micromouse is powered on, emitters will start to emit. And reflected signals will be detected and collected by our receivers. Collected data will be passed on to the ADC, and that data will be processed. Once the data is processed by ADC, it will be stored in the ADC's buffer. Processed data from the ADC buffer is used to control and adjust PWM for both motors. In addition, there's one more thing that we're using, one more module that helps us to make more precise turns. That module is called gyro, and my colleague Boris will elaborate more on that. Thank you.
Yeah, so we're using a gyro to measure our rotational movement within the maze. And the gyro actually outputs the change in angular motion. So basically, you take the gyro output, or the gyro has an error that's associated with it, more commonly known as yaw drift. So once you take the output from the gyro, you have to subtract that yaw drift from the value. You get a corrected value, and you add up that value that you get over time, and then you can get a reasonable estimate for your change in position. So this is how we're able to make very precise turns within the maze. And Steve's going to talk more about motors and encoders.
Hello everyone. So we wanted to pick DC motors for their high speed and lightweight capabilities. Our DC motors come in at 0.3 ounces, and have a no load output shaft speed of 30,000 RPM. They're mounted to a 10-to-1 reduction gear housing that brings that no load output shaft speed to 3,000 RPM. Now with these high-speed motors, we needed to get accurate speed and high-resolution data off the wheels in order to effectively control these. So we went with a integrated circuit that uses the Hall effect by using a Hall effect sensor that gets a differential voltage output by sensing the changing magnetic field in its proximity. Now, combined with a 22-pole pair magnetic ring that's mounted to our custom 3D printed wheels, this can generate 880 pulses per revolution. Now, you see here on the left is what's going on the inside of the IC of the magnetic encoder and magnetic rotary encoder IC. On the right is an actual O-scope screenshot of what the digital signal looks like. So the way our PIC32 is actually calculating the RPM, it's taking the number of positive pulse edges in that signal that's fed into an external timer. In this case, in this example, it's 15. It takes that, multiplies it by 60 for how many seconds are in a minute, divides that by the period of the interrupt, which in this case is 1 millisecond, and then multiplies that by the 880 encoder pulses per revolution. So in this example, it gives us an RPM of 1,023. So combined with this data for the speed of the wheels, we wrote an algorithm to effectively control the speed of the motors and to get it to drive straight. So what's happening is an error signal is created based on our desired velocity and the actual measured velocity of the wheel. That difference is then multiplied by a gain that we've empirically calculated in the lab by testing, and then that becomes a duty cycle, which is passed into the PWM function and determines the speed of the motors. So with this data and the use of the IR sensors, we can effectively drive straight and avoid the walls and solve the maze. Next up is Paul to talk about power management and PCB.
All right, so to power all of our components, we decided to go with the Turnigy lithium polymer battery, which provides our system with 7.4 volts at 180 milliamp hours with a max current discharge of 4.5 amps. We chose this battery because it perfectly matched our specifications, giving us approximately 10 to 12 minutes of actual operating time and only adding an additional 13 grams to our overall mouse weight. Now, to satisfy the different voltage requirements of certain components, we decided to include a 5-volt regulator, which will be powering the gyro, the XP, and the motor encoders, as well as a 3.3-volt regulator, which will power the PIC32, the IR sensors, and the H-bridge. So, in keeping with our compact and lightweight design goals, we decided to mount all of our parts onto a PCB chassis. This will act as the chassis of our mouse and keep all of our components organized and the overall dimensions of the mouse small. Now I'm going to hand it off to Boris to talk about the budget.
So we were allotted $600 to complete this project. We came in $16 under budget. Our biggest expense was the motors and the peripheral equipment that came along with the motors. We actually have a lot of spare parts, so as we get closer to the competition, we won't have any problems. So next to talk about the milestones will be Darren.
Okay, these are our milestones we set for our Micromouse project. Our first milestone being to complete our PCB chassis, followed by all hardware being installed and able to interface with the microcontroller. Next, we needed our mouse to be able to drive straight, followed by our mouse being able to navigate around corners while avoiding wall collisions. And then early this week, we finished our Micromouse. It is complete. It is able to navigate the maze and calculate its fastest time, all autonomously. And I'd like to thank all you guys for coming out to watch all of our presentations, even Dr. Harris in the front here, and Come support us on Thursday when we compete for the Micro Mouse competition.